No, there are no project presentations. Online, email. And I'll send out instructions for submission after we're done with the peer editing. Okay, so today I am going to give a lecture on the use of Markov chains for sampling and counting. The rough plan is about half an hour on the sort of general Markov chain approach, which I sort of sketched out last time talking about volume estimation. Then a half hour talking about counting bipartite matchings by sampling from bipartite matchings, which is also known as estimating the permanent of a graph. And then a half an hour on sampling from and counting the number of legal colorings of a graph, because these use two very different and interesting techniques, analytic techniques, even though they're both based on Markov chains. So general problem, our general approach is using Markov chains to sample. And sometimes you just want a sample from a distribution. Other times you are going to use that sample to do something. So counting is one canonical use. And a generalization of counting is computing partition functions, which show up all the time in physics. If you have an Ising model or a Potts model or a monomer-dimer model, the partition function is very important for understanding the behavior of that system. And the partition function is kind of a weighted counting problem. So the sorts of things that I'm going to talk to you about with counting can also be applied for computing these partition functions. Partition functions also show up a lot in machine learning, actually. And so this is pertinent there as well. And so in order to do this, we've seen how counting and sampling are related to each other and can sort of be reduced one to the other. But the challenge is then to generate a single sample. And I'm going to focus on the uniform distribution, right? There's some number of different items, and you want to sample one of them uniformly at random. The problem is that this is a very complicated distribution. It's not just a simple coin flip or something like that. And so it's hard to do that generation. And the Markov chain approach is to create a Markov chain whose stationary distribution is the distribution that you want to sample from. This is sort of changing the, right, the stationary distribution is sort of a global phenomenon of the state space, but the Markov chain is all about local moves. And so it is easier to implement those local moves than it is to just jump into this possibly exponentially sized state space and choose something out of it. So that's why Markov chains are useful for this kind of sampling. So the general idea is that you have some giant complicated state space. And a Markov chain lets you explore this state space via local moves. And if you can do it properly, you can design a Markov chain whose stationary distribution is the desired global distribution. Okay, that's great. The stationary distribution is the desired global distribution, but how do you get into the stationary distribution? Right? In general, when we think about Markov chains, we pick a start state, and then we start running the Markov chain. If you were able to sample from the global distribution, from the stationary distribution to pick your start state, then you would be in the stationary distribution and you would stay there. But if you deterministically pick a starting state, then you're not in the stationary distribution. How do you get there? Right? So the intuition is that a Markov chain eventually forgets its starting distribution or its starting state. Okay, and this makes intuitive sense, right? Sort of the action of if the evolution at each step just depends on the immediate previous state, then why should where you started long, long ago actually influence where you are now? Now, there are some exceptions to this. So for example, if you have a periodic Markov chain, right, then if you start in if you have an even-odd alternation, then if you start in an even state, then you're always going to be in an even state on even steps, and you're always going to be in an odd state on odd steps, and the Markov chain will remember that forever, which is one of the reasons we like to get rid of periodicity when we're designing our Markov chains. Right? But we'll formalize this intuition. And the question is, what is this eventually? Right? And so this takes us to the notion of a mixing time, which is how long does it take for the Markov chain to forget its starting state? And in most Markov chains, it never forgets it completely. It's just that the influence of the starting state becomes smaller and smaller over time until you can eventually ignore it. Okay? And the way that we measure this is if we have a stationary distribution that we would like to reach, and we have a distribution Q, then we can talk about the relative pointwise distance or RPD, which is just equal to the max over all states J of the difference in probability on that state between the two distributions versus the actual stationary probability. Okay? And of course, if the relative pointwise distance is 0, you're at the stationary distribution. But if you're not at the stationary distribution, there'll be a positive pointwise distance. But if it is less than epsilon, right, that means that the absolute value of qj minus pi j over pi j is less than epsilon, which means that the absolute value of qj minus pi j is less than or equal to epsilon times pi j, right? Which means that qj is in the range of 1 plus or minus epsilon times pi j. So every point has roughly the correct probability. And in fact, you can also say that 1 minus epsilon times qj is less than or equal to pi j. Actually, I should say 1 over 1 plus epsilon if I want to be really precise about this, right? Which means that you can write pi j you can write qj as wait a minute, which order do I want to say this? If I want to multiply say qj, let me say what I want to say, and then figure out how to derive it. So what I want to argue is that essentially qj can be written as mostly pi j plus some positive error terms. Okay? And that means that I can think of sampling from qj as with high probability sampling from pi j and otherwise sampling from some weird probability distribution. Okay? Right? And so if I can get a qj that is close to pi j, it is like saying with high probability I am sampling from pi j. And so I can say that, with high probability, I get the behavior that I would get if I sampled from the stationary distribution. Is that clear? I see some puzzlement. Yes? This is absolutely true. So, right, so I haven't said with high probability in what, right? And the point here is that epsilon becomes the probability that I am making a mistake, right? And yes, if I wanted something that was so unlike, like the number of states is not the thing that I'm probably going to care about here, right? I'm going to say, I want to generate a sample, I want to generate a random matching. Okay, so here's a process that will generate a random matching with probability 99%, right? And there's a 1% chance that it will not be a random matching, but it is probably a random matching, and I can use that for whatever purpose I want to use. We are not, in this application, generally trying to get something that works in every state, where we would have to take a union bound over all of the states. We are just trying to get one sample or a small number of samples to do something. Okay? But for example, if I decide I need to average together n samples for some purpose, right, then I would want the chance of error to be less than 1 over n so that all of my samples are likely to be from that stationary distribution. Okay? All right, so our goal is to argue that, or to understand when and how there is a mixing time such that if you run for the mixing time, your relative pointwise distance becomes less than epsilon. Because at that point you can stop and take whatever state you're in and say that is my sample from the stationary distribution. Is that clear? Okay. So why should there be a mixing time? And why might it be small? So there are a couple of different ways to argue that a Markov chain has a small mixing time. The first method is to look at eigenvalues. So this is called a spectral method. Okay. We have this transition matrix. P, right? Where the next state, or the next distribution at time t plus 1 is equal to the distribution at time t times the transition matrix. Yes? Pi is an eigenvector of P. With eigenvalue 1, right? Because pi p is equal to pi. And in fact, the way I stated the fundamental theorem of Markov chains, that there is always a stationary distribution subject to various technical conditions, right? That actually, right, the more direct way to state it is that a stochastic matrix always, with certain conditions, always has an eigenvector with eigenvalue 1, which of course serves as the stationary distribution. Now, the mixing time is bounded, or sorry, is determined, or is, let's see, what's a good word here? Let's say focuses on the second largest eigenvalue. Lambda 2. Okay, yeah? Oh, yeah, maybe I should put it over here so that we don't have to. All right. So the mixing time focuses on the second largest eigenvalue, and you have to be a little bit careful about this. The matrix can have negative eigenvalues, and some of them might be. So you care about the absolute value of the second largest eigenvalue. But first of all, notice that no lambda I can be bigger than 1. Okay. The reason is that suppose that you have some eigenvector EI, and you have a lambda I that is bigger than 1, right? If you look at the largest value, so essentially what's happening on the left-hand side with the transition matrix, right, because it's a stochastic matrix, you're just averaging you're creating a weighted average of the values of EI, right? Each value on the right is a weighted average of the values on the left, which means that the maximum value on the right can't be bigger than the maximum value on the left, right? And so if you were multiplying by something bigger than 1, you would end up with a maximum value for lambda EI that is bigger than the maximum value for EI, which would be a contradiction, okay? So you can't have any bigger than 1 eigenvalues. Okay. Now, if you have another eigenvalue, if you have an eigenvalue which is equal to 1, that's another stationary distribution, right? And the fundamental theorem of Markov chains says that subject to these various technical conditions, you can't have another stationary distribution. If you have, and similarly, you can only have a eigenvalue of -1 if the Markov chain is periodic. Okay, so these are ruled out. Otherwise, ruled out by technical conditions. Technical conditions of the fundamental theorem. So now we're in a situation which means that all of the lambda i's have absolute value less than 1. Okay. Now we know from our theory of eigenvalues and eigenvectors that since Q, our current probability distribution can be written as a sum of coefficients times eigenvectors, right? Everything is a combination of eigenvectors. That means that Q0, so Qt is then the sum of AI times EI times lambda I to the tth power, right? And so all of these lambda I less than 1 decay exponentially. So that all that you're left with is the part of Q that goes with E1, which is pi, the stationary distribution. Okay. And from this, you can actually conclude that A1 has to be equal to 1, because everything else is going away, but Q has to stay a probability distribution. It has to sum to 1. So you have to have the stationary distribution itself in the decomposition, and then you have some noise which decays exponentially as the Markov chain executes. Okay? So in particular, right, if lambda 2 is less than 1 minus 1 over a polynomial, for whatever quantity, or whatever variable it is that we care about, right, then a polynomial number of steps will decay all of the lambda i's to being negligible. And you'll be essentially close to the stationary distribution. So the problem of showing that a Markov chain has a small mixing time, a polynomial mixing time, comes down to the problem of showing that the second eigenvalue of the Markov chain is small. And just a little bit small, right? Just a little bit less than 1 is enough to give you a And so if this is true, if you have a polynomial number of mixing time, this is what's known as a rapidly mixing Markov chain. Clear so far? Okay. So now we have a method for showing that Markov chains mix rapidly, but it's a linear algebra method, and I don't like linear algebra, right? And I think combinatorialists do not like linear algebra. So the question is, can we relate this eigenvalue characterization to something more combinatorial? And the answer is yes. I think I've mentioned expanders before. Yes? Yeah? Oh, well, remember, this is purely analytical, right? I don't actually need to run the Markov chain using the matrix. Oh, so right. So the way you use this argument is you prove that the second eigenvalue is small. You don't actually compute the second eigenvalue. You prove that it is small for some reason about the construction of your Markov chain. All right. And then you don't need to write it down. Right? Then you just run it. So I think I've mentioned expanders before. Yes? Right? So these turn out to be very closely related to this eigenvalue concept. Okay? So there are various different kinds of expanders, and I don't want to go into all of the different details. But the general idea of an expander is that for any subset S of vertices, the size of the neighborhood of S is more than 1 plus some constant times the size of S. Okay. And so neighborhood here can mean a few different things. It could mean the number of vertices that are neighbors of S. It could also just mean the number of edges leaving the set S. And again, I don't want, so there's edge expanders, there's vertex expanders, you can talk about expanders as a bipartite graph expanders, or you can talk about general graph expanders, right? The important concept of expanders is simply that there is that any subset has a lot of stuff right outside of it. Okay, and the key theorem is that you have an expander if and only if that second eigenvalue is bounded away from 1. So there's this beautiful relationship between the combinatorics and the linear algebra, the spectral behavior. Okay? It also relates to another thing that we've talked about before, sparsity of cuts. Right? Remember that we talked about the min ratio cut, which is just equal to the minimum of the sort of number of edges crossing divided by the smaller side times n up to constant factors, right? Because one of the two sides is at least n over 2, so we might as well treat it as n, right? And if you think about it, saying that you have a lot of edges leaving every subset is saying that there is no small ratio cut, right? And I'm not going to be doing a lot of careful math this lecture, so I don't want to get into the exact values that we're talking about. I just want to point out that if you can show a lower bound, an appropriate lower bound on the ratio of a graph, then you have shown that that graph is an expander, which shows that it has a second eigenvalue that is bounded away from 1. And that shows that Markov chains on that expander, in other words, a random walk on that expander, is rapidly mixing. So this gives us a purely combinatorial way of demonstrating that a Markov chain is a rapidly mixing Markov chain. Okay. And these things are actually not really hard to prove, but they involve a lot of calculation. Lots of Cauchy-Schwarz inequalities and things like that, which I do not want to spend time on. All right. I think the intuition behind it, though, is very clear, right? So the idea of an expander is that any subset that you're looking at, there's a lot of exit from that subset. So think about what that means for a Markov chain. If most of the probability of the Markov chain is currently, if there's just a small number of states that are currently too likely, right? Well, a lot of the probability of transition, a lot of the transitions are going to take you out of those states to other states. And so the sort of location, your location in the graph rapidly becomes unclear. Because if there's any certainty about it, you can talk about the departure of probability mass from the place where you think the state currently is. Okay. All right. So that's all I want to say about the sort of connections here. What I'm going to be doing next is starting to talk about how you approximate the permanent. And all I need to do is give you a Markov chain that has the right stationary distribution, and then argue that the graph of that Markov chain is an expander, has a large sparsest cut. Okay. And you can find plenty of details about this in the textbooks or ChatGPT or whatever works for you. Yeah, and actually some of this was worked out, I think, in the context of what I'm going to be talking about next, which is approximating the permanent. So what's the permanent? Well, remember the determinant of a graph is a sum over all perfect matchings of -1 to the sine of the matching, right? Matchings are permutations. They have odd and even signs, times the product over all of the, sorry, not over perfect matching, sum over pi of the product over AI pi of I, right? So the determinant is something that you compute over a matrix. You take all of the permutations of the rows and columns, and you take a product of all of the elements in the permutation, right? We used this at some point in the semester, right? Right, for perfect matchings, for the Tut matrix. The permanent is the same thing, except without the -1 to the power of sine of pi. Okay, so you just take all of those same products, but instead of adding and subtracting, you just add them all up. Okay. We all know that the determinant is easy to compute. So surely the permanent is also easy to compute, because it's pretty much the same thing. No, sadly, computing the permanent is sharp p hard. Okay, probably harder than NP. Okay. as a special case, right, if the matrix is an adjacency matrix of a graph, then of course you only get a non-zero value here when you have ones all throughout the permutation. In other words, if you have a perfect matching. So if the permanent of an adjacency matrix is just equal to the number of perfect matchings. Of a graph. All right. And so I'm going to focus on, right, so this is also sharp. Just counting perfect matchings is also sharply hard. But we're going to get I'm going to sort of show you how to get a fully polynomial approximation scheme using Markov chain sampling. And this was a big breakthrough in the late 80s, I think. And they came up with an FPRAS for dense graphs, which have min degree n over 2. And that is, you'll see why that condition is very useful to us in just a minute. In the 2010s, they figured out how to generalize this to all graphs. And I don't think it required any really deep ideas. It just required more care and some sort of technical lemmas to generalize it. So I think that the main ideas are from this work in the 1980s. This idea, it sort of first came out from a guy named Andre Broder. And he published a paper which sort of demonstrated the core idea of using the Markov chain to sample. And then it turned out that his proof that it worked was broken. But Jerram and Sinclair, shortly thereafterwards, gave a correct proof of the rapid mixing of the Markov chain that Broder had defined. Okay? So you kind of credit them for this together. So we'll work our way into this a little at a time. First of all, I'm going to argue that you can use self-reducibility here to go from generation to counting. So I'm going to reduce the problem of counting to the problem of generation. And you've done this before. You did this in your homework, right? When we talk about sampling disconnected graphs and so on and so forth, right? So what we do is we find an edge, and we use sampling to estimate the number of matchings, or the fraction of matchings using that edge, right? We then discard that edge and vertices and recurse on the graph that is left. And then we scale by that fraction. Right? If half of the matchings use this edge, then after we throw away the edge, we count the matchings in what's left, and then we double it. And that tells us the total number of matchings. Right? This is exactly like you did in your homework. So is that clear? That in order to count, all I need to do is generate a perfect matching? There are some details, right? If the edge is, if the fraction for that edge is tiny, right? Again, just like in your homework, if the fraction for that edge is tiny, then you've got a problem because you may never see occurrences of that edge in your generated matchings. But you can sort of use a pigeonhole principle to argue that there is some edge that's relatively common in matchings, as in at least 1 over n or 1 over m of the matchings, that its fraction is at least 1 over m. And so you only need order m samples in order to see which edge that is, and you can use that one as your for your self-reducibility. Okay? So everybody comfortable with the idea that if I want to count, and again, counting is equivalent to partition function calculation as well, right? So that may very well be the problem we want to solve, but I've shown you that in order to do that, all you have to do is generate. Yes? So now we just talk about generating a perfect matching. So given what I've set up over here, you would think that the way to generate a perfect matching is to create a Markov chain on perfect matchings. Right? Problem is that nobody's come up with one. Right? You need a notion of local moves in order to define your Markov chain, right? Which means you need some process that takes one matching and takes one perfect matching and gives you a different perfect matching. Okay. And I mean, we have such processes, namely augmenting paths or augmenting cycles, right? But they're not very local, right? To move from between any two, the point is that between any two matchings, there's a collection of augmenting cycles that will transform one of those matchings into the other, right? And this is actually relevant for later. So let me point that out, right? That if you have two matchings, S and T, they differ, right? Their XOR is a set of cycles. Okay? The matchings will agree on certain pairs, and so of course those will vanish. So what you're left with is two matchings that don't agree anywhere, right? And each of those matchings induces a degree of 1 on every vertex, which means that if you put the two matchings together, you have a graph which has degree 2 on every vertex. Yes? And the only way to have degree 2 on every vertex is to have a cycle or a collection of cycles. Okay? So this tells you how you can get from one matching to another, which is you just sort of rotate that cycle, right? You swap from the odd edges of the cycle to the even edges of each cycle, and that gives you, but that's not a very local move. You're changing tons of edges all over the graph, right? So Broder's insight was, not surprisingly, to grow the state space. Okay, if your current distribution, if your current states are complicated, make a bigger state space. We've used this trick before. So Broder's idea was to make a nice Markov chain on perfect matchings and what I'm going to call imperfect ones. One less edge. Than a perfect matching, right? So we'll say n here. This will have n minus 1 edges. Our graph has 2n vertices. Okay? And the claim is that if you take this larger collection of perfect and imperfect matchings, then there's a natural local move Markov chain on this collection of states. Okay. And so let me show you what that Markov chain looks like. What you do is, you pick a random edge E of the graph, not of the matching. Okay. Then, if you are currently perfect, you have a currently perfect matching S, and E is in the matching, remove it. You've just changed from your perfect matching into an imperfect matching. If you are currently imperfect and you can legally add E, do so. What does it mean that you can legally add E to your imperfect matching? Yeah? Exactly. Its two endpoints are unmatched. Okay. Otherwise, if you are imperfect, if you are imperfect, let me put it this way. Else, if you chose UV, where U is matched to W and V is unmatched, then move U to V. Okay? So if you previously had a UW and you are now picking a UV, you simply switch the other endpoint of U to use the edge that you just picked. Okay? So right, so this is changing you to a different imperfect matching because now W is unmatched, right? It's kind of like cuckoo hashing in a way, right? Okay. Else you do nothing. And there are various reasons that you might do nothing. And if that happens, you just stay in your current state. And that creates a self loop, which also makes the graph, which makes the Markov chain aperiodic, which you want anyway. Okay. And so the claim, of course, since there is an else at the bottom, or sorry, actually, these three cases are exclusive of each other, right? And the last case covers everything else. So there's exactly one thing to do depending on which edge you chose. Okay. So now the interesting question is, what is the stationary distribution of this chain? Well, this is actually a very nice chain because it is reversible. Okay? Every action that is described here in the Markov chain has an equal and opposite action that undoes it as a possible next step, right? So here I have, right, these two actions are inverses of each other, right? And for this action of, right, if I pick UV, I move from UW to UV. Well, in the next step, I can pick UW and move from UV back to UW. Okay? So this is a reversible Markov chain. And so in your homework, you proved that this has a uniform stationary distribution. Right? So this simple chain of just fiddling one edge in each step gives you a uniform stationary distribution over the combination of perfect and imperfect matchings. Yes? Great question. So we need that property, right? We need this Markov chain to be connected, right? Which means that there needs to be a series of local moves that will transform any matching or imperfect, any perfect or imperfect matching, into an arbitrary other perfect or imperfect matching. I'm going to concentrate on the perfect matchings just to keep it simple, right? So is there a path from S to T, two different perfect matchings? And the answer is yes. We've already said that the XOR of this is a set of cycles, right? I claim that you can use local moves of this Markov chain to unwind each cycle, okay? What I do is I look at a cycle that is the result of the XOR, right? And so half of its edges belong in S. Sorry, I should have used S and T rather than 1 and 2. Half of its edges belong in S, and half of them are part of T, right? So suppose that I start at S, right? So I initially have the 4 edges of S. Okay. What do I do? Well, first I use the reduce to an imperfect matching step, right? By throwing away an edge of S, right? So this goes, and I have these 3 edges remaining. Yes? Now I have 2 vertices that are not matched. So now I use the steal local move, right? The next thing that happens is I steal I steal the next vertex along the cycle, right? That frees up another vertex, which can then steal the next vertex along the cycle. I hope these diagrams are making some sense, right? I do one more steal, right? I guess what will make it have more sense is if I add the other missing vertices. I do one more steal. Now I've got back all but one of the edges of the perfect matching of T, and finally I use an insertion of an edge to complete the perfect matching. Okay? So I'm going to refer to this as unwinding a cycle. And it's going to be important later. But it does show you that we have connectivity of all of the perfect matchings are connected to each other, right? You can use a similar argument to show that the imperfect matchings are also connected to the perfect matchings and to each other, okay? All right. Now there's another thing. So we have a Markov chain. Its stationary distribution is uniform 1, which means that if we wait for the mixing time, we can get a random sample from this Markov chain. Next thing to worry about is the rare event problem. Okay. What if we keep on sampling imperfect matchings, right? In order to do our self-reducibility, we need perfect matchings, right? The imperfect matchings are noise or distraction, right? So we have to worry whether perfect matchings, I'm just going to call this Mn, matchings of size n, are much less than the imperfect ones, which we'll call matchings, which we'll call Mn minus 1, right? So if this is tiny, then we'll keep getting these and we'll never succeed in sampling perfect matchings and we won't be able to apply our self-reducibility. Okay? This does not happen in dense graphs. And this is why the original breakthrough on counting bipartite matchings was restricted to dense graphs. It was for this property that the perfect matchings are not rare. Okay. the idea is pretty straightforward. I'm going to create a mapping between perfect and imperfect matchings that does not assign too many imperfect matchings to any perfect matching. And that will show that there's a decent number of perfect matchings. Okay. I can map each mn to some of the m sub n minus 1s by deleting an edge, right? This transforms any perfect matching into an imperfect matching, right? There are only n ways to do this, right? N edges to remove, right? I can also map each imperfect matching to a perfect matching using an augmenting path of length 3, which I will now show you. Suppose that U and V are unmatched, okay? Because we have an imperfect matching, okay? What's that saying? Right. U and V both have more than n over 2 neighbors. That's the assumption. Okay. So if they're all matched, then some neighbor, I'll call it B, of U is matched to some neighbor A of V. Right? I've got U and V. They're not matched. Okay. But U has lots and lots of neighbors, right? More than n over 2 vertices that are neighbors. V also has more than n over 2 neighbors, right? And if any of them are not matched, then I can just match V or U. But if both of them have all of their neighbors matched, right? Here I have more than n over 2. Here I have more than n over 2, which means that that some pair of these are matched to each other. And that means that I can make an augmenting path of length 3. I can unmatch these neighbors from each other, and I can instead match them each to U and to V. Okay. And so the result is that I can transform, I can give every imperfect matching to a perfect matching by shifting 3 edges around, right? There are at most m cubed ways to shift 3 edges like this. And that means that each perfect matching only receives m cubed imperfect matchings. Yes? Yeah, I mean, we're just dealing in polynomials here, so not too worried about the exact polynomial. So what this shows is that the imperfect matchings can only outnumber the perfect matchings by a polynomial factor, which means that within a polynomial number of samples, I'll get a perfect matching. Okay. So that kind of completes all the preliminaries. It says, we've got this Markov chain, it has the right probability distribution, and the perfect matchings in it are common enough that we can use it to sample perfect matchings. So the only question that remains is what is the mixing time, right? So let me leave you on tenterhooks for a moment. We'll take a short break. We'll take a 2-minute break, and then I will show you the mixing time analysis. Yes. Like, are you? Yeah, yeah, yeah. Yeah, yeah. Sure. Yes, yes, yes. I mean, we should discuss it after I've had a chance to look at your project and such, because it'll be good if I can use the project as the basis for the recommendation. Yeah, but at a minimum, I mean, are you doing a reading project or a research project? Are you doing a reading project? Yeah. Okay. I mean, at a minimum, I've written lots of recommendations to just talk about the class and its level, and people who do well in it tend to go on to do great stuff. Ideally, I'll also be able to talk about your project being excellent and so on and so forth. Okay? Okay, let's resume. The problem that remains is to show rapid mixing, and as I set this up, right, what that means is we need to show that the graph of this Markov chain is an expander. Or in other words, that the smallest ratio cut is large, right? So we show rapid mixing via a large ratio cut argument. Okay. And Jeremy Sinclair developed a new technique for proving this called the canonical path argument. Which is a really interesting way of demonstrating ratios, which essentially relies on max flow min cut. Okay. The idea is, suppose we have an n vertex Markov chain. Okay. And we want to prove that every subset S has omega of S edges leaving it. Okay. Right? That's going to give us that's the ratio that we need in order to, and the constant here is actually what determines the mixing time. Right? If you have twice as many edges leaving each set, then it halves the mixing time, because things get out twice as fast. Okay? But, I mean, this is a constant from the perspective of n, but for us, it's actually enough for this to be like 1 over a polynomial, right? Because then the mixing time will still be polynomial. Okay? In polynomial in n, the number of vertices of the graph, right? Because that's the quantity that we are measuring against. Okay? So even size of S over poly of n gives a poly of n mixing time. Okay. So the way that we do that is we define a path between each pair of vertices of the n vertices in our chain. This gets a little confusing because we've got the graph of the Markov chain and we've also got the underlying graph. But right now I'm just talking about the Markov chain. Right? We show that no edge is used by more than some poly in n times capital N paths. Okay. We know that size of S times n minus size of S paths leave S. And this is bigger than S times n over 2, which implies that at least, right, if we have this many paths leaving S, but no edge can carry more than polynomial times n paths, that means that we have at least Sn over 2 divided by that polynomial in n times n edges, which is more than S over poly of n. Edges have to leave S, and our analysis is done. Right? So essentially what we're doing is, if you're familiar with this, we're defining a multi-commodity flow problem. Right? We're saying we need to get a path or a unit between every pair of vertices. We have a route for each of those pairs of vertices, and no edge is carrying a lot of flow. Therefore, in order to carry all of the flow that is leaving a set S, because there is a lot of flow leaving set S, there must be a lot of edges available to carry that flow. Does that make sense? And again, I'm like, this is the kind of thing which to do carefully would take 3 lectures. So I'm trying to give you the picture without giving you the numbers. And if that is confusing, tell me. And I think I can make the picture unconfusing even without the numbers, but only if you tell me what's confusing. So modulo, why a polynomial here, is it understandable why we sort of achieve our goal by just showing that there is not a lot of edge congestion from these paths that we have defined? Yes? Okay. So that was a really cool insight and a quite general insight. They then came up with a collection of canonical paths that I have no idea how they came up with it. And even more interesting is how they showed that it's low congestion. So what is the canonical path construction for matchings? So remember, we have to, and I'm going to again focus on the perfect matchings. The canonical path for imperfect matchings starts by going to its perfect matching neighbor through these 3 augmenting path steps, and then onward. But this only adds a congestion, an m cubed congestion, so we're not going to worry about it. Right? We're not worrying about these polynomials right now. Okay, so the real question is how do you move between 2 perfect matchings? Right? What we do is we have 2 matchings, S and T. We XOR them. We already know that this produces cycles. We talked about this before, right? So now I'm going to order all vertex subsets lexicographically, which is also going to order the cycles. And I actually don't care what the order is. I just need an order. Okay. And the path is simply to unwind the cycles of the difference in order. And to start unwinding each cycle, by removing the edge incident on the smallest vertex of the cycle. So again, this is arbitrary. It's just to enforce a deterministic rule. Okay? So again, we talked before about how you unwind a single cycle by removing one edge and then rotating edges and then putting back the last edge, right? We're just adding to that rule which vertex you start with so that it's unambiguous. And then we're saying to get from one matching to another, you unwind all of the cycles in order. Clear? Okay. So that defines the paths. Now, how do we prove that each edge is not using a lot of, that there are not a lot of paths using any edge? So their lemma is that fewer than n paths use every edge. Sorry, this is paths between perfect matchings. Once you throw in the imperfect matchings, that multiplies this by an m cubed power, but we don't care about that polynomial. Okay. So the point is that if you only look at the paths, if you look at the paths from their perfect matching endpoints, there's only n of them using a particular edge. And the proof, this is very circular, is they give a bijection between paths using a given edge, E equal, let's call it Q comma R, right? So if you want to show that there's at most n paths using this edge, what's the natural thing to biject with that we have n of? Well, perfect matchings. So this is weirdly circular, right? So what they're going to do is they're going to say, we're going to look at all of the paths that go through this edge, and we are going to associate each of them with a different perfect matching. And that will prove that the number of paths through the edge is bounded by the number of perfect matchings. Yes? Okay. How do we do that? So given the path endpoints, S and T, we know that the XOR is a set of cycles, right? If the path goes through the matchings Q and R, right? It's an unwinding path, right? So it's taking out some edges from S and slowly replacing them with edges of T. So when we get here, we're going to have, right, that tells us that Q is a mixture of edges from S and T, right? Depending on where it is in this unwinding path, right? But it doesn't have other edges, right? what we are going to do is the matching corresponding to the ST pair is the XOR of S and T, which is a collection of cycles, XORed with Q. Okay. Q is a matching, which has some edges from S and some edges from T. So we now take these cycles, which consist of a bunch of edges from S and T, and we change Q through those cycles. And this is the matching M prime representing the pair S and T. And the claim is that this is a bijection. So first, is it clear why, if I take this collection of cycles that comes from XORing S and T, that XORing that with Q gives me another perfect matching? Because remember, Q is this sort of partial unwinding of S and T, right? Let's look at a particular step along this cycle here, right? So if you think about the ST cycle, which is on the same set of edges, right? You're essentially flipping which edges are here, right? Which is giving you another perfect matching, right? Except for the one cycle that's in the middle of being unwound, right? So you've got some cycles that look like this, right? And when you XOR them with the cycle difference, you just flip from the S edges to the T edges, right? For the one that's being unwound, you've got sort of a little glitch at the spot where you're in the middle of unwinding the cycle. Yes? So this shows that what you have here is a matching, again, -1 edge because of the where you're unwinding the cycle. But what's great about XOR is that you can go back the other way, right? And so this is going to show that you have a bijection, right? The claim is that given S XORed with T, all XORed with Q, which is the matching that represents the pair ST, you can reconstruct S and T. And that is because we have this canonical ordering of how we unwind cycles, right? So we're given S XOR T XORed with Q, but remember, we're decoding or reconstructing from the perspective of Q, right? So we can reconstruct, or we can compute S XOR T, right? This is a perfect matching that we have. We also are doing this from the perspective of QR, so we have Q, right? And so given Q, we just XOR with Q again, and we get back S XOR T. In other words, we get back the collection of cycles that represent the difference between S and T. Okay? Now, we can look at how those cycles relate to Q, because remember, Q is on the canonical unwinding of these cycles. So we'll have a collection of cycles, and we know which of them come before the cycle where Q is shifting an edge, and we know which of those cycles get unwound after the cycle where Q is shifting an edge. So the cycles of S XOR T that precede Q's cycle have already been unwound by the time that we get to Q. And that means that those cycles currently have the edges of T. And the edges that they don't have are the edges of S. Conversely, the cycles that come after Q have not yet been unwound in the canonical order, and so they still have the edges of S, and they don't have the edges of T. And then there's the cycle that Q is in the middle of unwinding, but because we know which vertex we started at, we can also see which of those edges belong to S and which of those edges belong to T. And so that completes the reconstruction, right? That just given this matching that encodes S XORed with T, we can reconstruct S and T. Yes?
What about the edges that are both in S and T and they completely canceled?
Well, that's just it. They're completely canceled, and so they never get unwound, and they don't show up in the canonical path at all. What? What was that? Well, remember that Q is on the canonical path, and so if you have an edge that's in both S and T, then it's never going to change, and it's still going to be there in Q.
No, but my point is, doesn't this mean that like multiple pairs of S and T could correspond to like the same M?
No, because again, the edges that S and T share are also going to be in the matching Q. Right? Because they never get taken out. They never get taken out during the canonical path transformation. So you can just read those out. You can just read those off of Q. So since we can map from any matching that has been encoded with Q to the pair S and T, that tells us that there is at most one pair S and T for each matching, which means that the number of pairs S and T is bounded by the number of matchings. So there are at most n of these pairs that use this edge through Q. Okay. And I know I skimped on the details, but this really is the central idea, and you can find all of the rest of it in the Jerram and Sinclair paper, complete with pretty pictures of all the unwinding circles. Okay. And that completes the story, right? We've shown that the conductance, that essentially, right, if you just look at perfect matchings, the number of edges is kind of proportional to S. Once you include the imperfect matchings, which adds a polynomial in M overload, then the number of edges leaving is like S over M to the 6th or something like that. And that is enough to give us the expansion that we need to get polynomial time rapid mixing, which gives us polynomial time sampling of perfect matchings, which gives us a way to approximately count perfect matchings. And we're done. So, any final questions? Pretty cool result, yes? I mean, the really general things that you can take away from this are these ideas of constructing a suitable Markov chain